Whenever you're working an equilibrium problem, whether it's a standard equilibrium, an acid-base equilibrium, or even a buffer equilibrium, it's always helpful if we can simplify. But when do you know when you can simplify? Well, if we take this example, and rather than find all of the equilibrium concentrations, what I'm going to do is I'm going to work this problem out both with simplification as well as with the quadratic formula in order to show you the difference in what the x values are. And I'm going to show you how to use the rule of 5. Now, our general rule of thumb, whenever you're looking at an equilibrium problem, if the initial concentration and the K value are more than 1,000-fold different, you can simplify. Just go with it. If you're close, you need to use the rule of 5. So what I'm going to do is I'm going to set this up so I have my change in my equilibrium. So the initial concentration here is 1 molar. The change is going to be some value x that I do not know. Then we can set up the equilibrium. So I have my 1 minus x, my x, my x. So my k expression, and this is going to be the k expression for simplification or non-simplification, is going to be the product of my products over the product of my reactants. So again, if I then substitute here, I have x times x over 1 minus x, and that's going to be equal to 0.0211. So over here I'm going to simplify. So 0.0211 equals x squared over 1.00 minus x. So the simplification is going to be to remove this x, thinking that the x value is going to be so much smaller than the initial value that it's not going to make that big of a difference. That is the simplification I'm talking about. So then I have this as my equation. 0.0211 is equal to x squared over 1. So my x squared is equal to 0.0211. I take the square root of both sides and I get an x value of 0.145 capital M molar. Now we have the rule of 5%. So I take my x value and I divide it by my initial concentration, and then I'm going to multiply it by 100 in order to get a percent value. This works out to 14.5%. Because the x value I calculated is more than 5% of my initial concentration, I cannot simplify. I must use the quadratic equation. So here I'm going to set this up again. So now I have my x squared is equal to 1.00 minus x equals 0.0211. Now I'm not going to simplify. So I'm going to multiply through. So x squared is going to be equal to 0.0211 minus 0.0211x. Then I'm going to put all of my pieces here on one side so that the equation is equal to 0. Now I can use the quadratic equation. Now the quadratic equation gives us an x is equal to the negative b plus or minus the square root of b squared minus 4ac all over 2a. Now what that means is, and I'm going to highlight, my a term is the coefficient in front of x squared. So these a's become 1s. My b term is here, and the sign goes with it. It's a positive. So I'm going to substitute my b's there. Now my c term, the sign goes with it, is here. It doesn't have a variable with it. So you can do this the old-fashioned way. You can plug in your values. So you have a negative 0.0211. Why do we have a negative? Because there's a negative in the quadratic formula, even though that value is positive in my equation. So then I have this minus 4 times a is 1, so I'm just going to drop it off because anything times 1 is itself, times a negative 0.0211 because that's my blue c term. All of this is under the square root all divided by 2 times a, or 2 times 1, which is 2. Now when you do this, because of this plus or minus right here, you're going to get a positive number and a negative number. The positive number is the only one that could possibly be a root in an equation in a situation like this. Now x is going to be 0.135 molar. So you see we were off in the hundredths place, and that's enough for a problem like this. That's enough to lead you to incorrect concentrations. So the general rule of thumb, when your initial concentration and your K value are at least 1,000-fold difference, you can simplify, otherwise you cannot. So if we have the same chemical too, but we have an initial concentration of 100 molar, now we set up our ice table, and it's very similar, except now we have 100 minus x for our equilibrium. The K value is still 0.0211, and our expression is still formed the same way. So we have the x squared on top. This time we have 100 minus x on the bottom. Now our K value and initial concentration are more than 1,000-fold difference. If I multiply K by 1,000, 1, 2, 3, I get 21. And that doesn't hit my initial concentration yet, so I should be able to simplify. So again, I'm going to run the simplify over here, and then I'll run the quadratic over here. So in both situations, I have 0.0211 is equal to x squared over 100 minus x. Just going to simplify that out completely and drop the idea of significant figures for this moment. So when I simplify, what I mean is that this x is going to drop off. Not these x's need to stay, but the x that is going to be added or subtracted is going to be dropped off. So now I have 0.0211 equals x squared over 100. Multiply both sides by 100 to get x squared is equal to 2.11. Take the square root of both sides to get an x value equal to an x value equal to 1.45 capital M molar. Now when I run the quadratic, I get an x squared value is equal to 2.11 minus 0.0211x. Put everything on the same side so that we can be equal to 0, and then use the quadratic formula. When I use the quadratic formula, I find that x is equal to 1.44 molar. So you see, that difference isn't going to be as noticeable when our initial concentration is 100 than when it's 1. And so you have to look at scales here. If we go back to our rule of 5%, I have 1.45, my x value, over my initial value times 100, I have a 1.45%. So that is a valid simplification.